Stop.
Right. Hello, everyone. My name is Tana Thorne-Bursard, and today I'll be sharing with you our work title on the implications of choosing average versus marginal carbon intensity signals on carbon-aware optimizations. All right, so let's get started. So to begin this talk, let's look at energy mix and carbon intensity. Let's suppose we have a hypothetical electricity demand that varies with time, and this electricity demand is served by a different energy mix. So let's look at the first time period. The electricity demand is served by gas. In the next time slot where the demand is still increasing and there is solar availability, the electricity demand is served by gas and solar. In the third time slot where the demand is still increasing, the demand is now served by gas, solar, and coal. So with the energy mix, each energy source has different carbon intensity. And the definition of carbon intensity is carbon emissions per kilowatt hour of electricity, also expressed as grams of CO2 emitted per kilowatt hour. And just to give you some illustration here, so let's say we have 1 kilowatt hour of electricity. Solar would emit lower carbon emissions as compared to coal. And what this means is that solar has lower carbon intensity as compared to coal. Right. So when the generator serves the electricity demand, there are two ways to calculate carbon intensity. So the first one is the average carbon intensity, where you take the weighted average of carbon emissions of the energy sources with respect to their production. So let's look at an example here. Here, the electricity demand is served by gas and solar, and the average carbon intensity is the weighted average of the two sources. So marginal carbon intensity, on the other hand, is the carbon intensity with respect to the change in demand. So here, the next unit of demand is served by the coal generator, and the marginal carbon intensity is the carbon intensity to that of coal. Okay, so the two carbon intensity signals are used in many different decarbonization efforts, including workload shifting, where we want to shift the workload to when and where low carbon energy is available. And such carbon-aware optimizations are enabled by third-party services such as electricity maps and watt time that provide carbon intensity data across regions worldwide. And so far, we have discussed that the two carbon intensity signals are calculated differently. So our research question focuses on the implications of the choice of carbon intensity signal on carbon-aware optimization. And to do that, we look into two carbon-aware optimization techniques, including temporal and spatial workload shifting. We use data from electricity maps that include 65 regions from the year 2022 for both average and marginal data. All right, so let's look at temporal shifting. So here is the example average and marginal carbon intensity signals from Wyoming on a given day. And here you get to see that you can either use the average or marginal carbon intensity signal to schedule your workload. So if you use an average carbon intensity signal, you would shift the workload to the low carbon period based on the average carbon intensity signal as the following. But from the perspective of marginal intensity signal, this low carbon period of one signal is a high carbon period of the other. And similarly, when you want to use marginal carbon intensity signal as a scheduling signal, you want to shift the workload to the low carbon period of the marginal carbon intensity. But on the perspective of the average carbon intensity signal, this is the high carbon period. All right, so let's look into some results. So here, the figure on the right here shows when the marginal carbon intensity signal is the scheduling signal. And when we use the marginal carbon intensity as a scheduling signal, the mean carbon savings across 65 regions is at 11%. But on the perspective of the average carbon intensity signal, the mean savings are negative. And what this means is that there is an increase in carbon emissions from the perspective of the non-scheduling signal. And while the result here only shows when the marginal carbon intensity is the scheduling signal, using the average carbon intensity signal yields the similar result, and more details can be found in the paper. All right, let's look into spatial shifting. So let's say we have a workload at origin X, and we want to reduce the carbon footprint of this workload by migrating the workload to two of the regions, either one of the regions, so region A and B. Now consider the case where the average carbon intensity is the scheduling signal. So here you would want to migrate the workload to region A, right? And however, if you consider the marginal carbon intensity signal, you will want to migrate the workload to region B. Okay, so let's look at the impact of spatial shifting. So again, on the figure on the right here is the result when we use the marginal carbon intensity signal as the scheduling signal. So here you can see that with, oops, there's a typo there, sorry. This is a marginal carbon intensity. So when you use a marginal carbon intensity signal as a scheduling signal, the mean savings across 65 regions is 87%. However, on the perspective of the average carbon intensity signal, the carbon savings is lower. And again, we also have a result of that. We use an average carbon intensity as a scheduling signal, and it used similar result of carbon savings around 87%, and you can look into more details in the paper. All right, so to summarize, in this work, we perform temporal and spatial workload scheduling. And the two signals result in different scheduling decisions as well as different carbon savings. So to end this talk, which signal is the best? So far, this is an open research questions because it is unclear about which workload we should use for different kinds of signal. But what I can say is that the best signal, to determine what is the best signal, I would say that it is a signal that gives the largest system-wide carbon reduction. And to do this, we would need to examine the system in a global scale rather than each individual systems. And that I conclude my talk. Thank you.
Hey, thanks for the great talk. My question is a bit more fundamental. Do you think it makes sense moving forward in computing, carbon computing, to optimize for carbon intensity at all? Because I think average carbon intensity, we know, is a pretty poor metric. We heard it in this discussion. It hides all the complexities of how power grids work, how electricity markets work. And average carbon intensity is always based on estimates. It's always based on predictions. And according to my experience, whenever electricity maps over time, when they introduce a new methodology, everything changes. So it's really vague. So both metrics are pretty poor. Does it make sense that we continue to develop approaches that optimize for these metrics?
Yes, I think we should, but I think we have to go back one step before to even optimize. I think we should be able to measure things in a more accurate and precise manner. So maybe we should start from there and we'll take it from there. So measure first and then we optimize. Yeah.
Hi, thanks for the great talk. This might be a bit of a naive question, but is the marginal carbon signal even available at the moment? Because that would mean knowing which generator will come on if I move something.
Right. So some of the grids actually give you the marginal sources, but it's not available for all the grids. So most of the time it is a model that I will stop clicking. Yeah, so there is for some grids they do publish the marginal data, but not every grid has that. Yeah.
Okay, thank you.
Yep.
Our last paper